Last video we solved these with the augmented matrix method. Here I'm going to show you how to use Cramer's rule to solve for it. Cramer's rule is very good for solving for one variable, but it takes kind of tedious to solve for all of them. So let's write. I guess we can write our augmented matrix: 1, 2, 1, 1, negative 2, negative 2, negative 1, negative 1, 1, 1, 1, negative 1. Alright, so let's say we want to solve for x. X would equal the determinant of ax over the determinant of a. Now, what do I mean by ax? Ax is the matrix where the solution replaces the x column. So ax would look like this. It would look like 1, negative 1, negative 1, 2, negative 2, 1, and 1, negative 1, 1. Okay, now that means, so this was our answer column, but it's now in our x column. Okay, so we replace whatever we want to solve for. So if we wanted to solve for y, we would put it here. If we want to solve for z, we would put it here. So you put the answer column where you want to solve it, instead of leave everything else the same. You take the determinant of that divided by the determinant of the original. Let me just show you what that means. So let's get the determinant of a would be 1 times negative 2 plus 1 minus 2. Now I went over how to take the determinant in the last video, so if you're a little iffy on this, please refer to that. It's going to be negative 2 plus 1 plus 1 times negative 2 plus 2. So this is 0. So we're left with 1 is going to be negative 1 plus 2, which equals 1. So the determinant of a is 1. Awesome. So now let's take the determinant of ax. It'll be 1 times negative 2 plus 1 minus 2 times negative 1 plus 1, minus 1 plus 1 times negative 1 minus 2. So here we're left with, there's going to be a negative 1 plus 4. It's going to be 3 minus 3 equals. So we're left with negative 1 plus 4 minus 3, which equals 0. So x equals 0 over 1, which is 0, and that's what we got in the last video. Now we can easily solve for y will equal the determinant of ay over the determinant of a. Now we already know the determinant of a is 1. So all we have to do is the determinant of ay. So ay would be the matrix where the answer is plugged into the y column. So we're going to do 1, negative 2, 1, and then the answer column 1, negative 1, negative 1, 1, negative 1, 1. Awesome. So now let's just take the determinant of that, and we'll be set. So determinant of ay equals determinant of ay would equal 1 times a negative 1 minus 1 minus 1 times negative 2 plus 1 plus 1 times a 2 plus 1. So this would give us negative 2 plus 1 plus 3, which would be 2. So y equals 2 over 1, which is 2. So that's pretty simple, pretty straightforward. you'll probably be given the determinant of a, so the determinant of have to find one of these values, not all three, which would be a little time inducive. So let me just solve z, let me just solve z real quick so I can see it done one more time. So z would equal the determinant of az over the determinant of a. So az would look like 1, negative 2, 1, 2, negative 2, 1, and then now the answer column here, 1, negative 1, negative 1. Awesome, so now I can take the determinant of az would look like 1 times 2 plus 1 minus 2 times 2 plus 1 minus 1 times negative 2 plus 2, so this goes to 0, so this would equal 3 minus 6, which is negative 3, so z would look like negative 3 over 1, which is negative 3. Alright, so that's how we solve using the Cramer's rule. I think that's enough example to go with that. So just remember to replace the column of the one you want to solve, the variable you want to solve with the answer column instead. Eigenvalues and eigenvectors. Now, to get the eigenvalues, I'm going to write the actual mathematical whatever of it. Determinant of a minus lambda I has to equal to 0. It's a fancy way of saying the determinant of a with lambda subtracted down the diagonal has to equal to 0. Let me just write it out. So it's going to be the determinant of 1, 0, 2, negative 2, that's a, minus lambda times 1, 1. That's what I mean. It's the fancy word, I don't remember what it's called. So then this looks like the determinant of 1. Now this lambda gets distributed all the way through, so you get lambdas there, so you're left with 1 minus lambda, 0, 2, negative 2 minus lambda. So like I said, it's just a fancy way of saying a lambda subtracted across the diagonal. So the determinant of a 2 by 2, I don't know if you remember, it's just the first diagonal minus the second diagonal. Kind of like the Ron scheme we did on the last test. So this would be 1 minus lambda times negative 2 minus lambda minus 0 times 2 would have to be 0, so that goes away, so then we're left with 1 minus lambda, negative 2 minus lambda. As you see, I haven't factored it out because there's no, since this is 0, it's already factored out, so we don't need to distribute to factor it out. So now we get lambda equals 1 and negative 2. Now I'm going to label them lambda 1 equals 1, lambda 2, eigenvalue u2 equals negative 2. So to find the eigenvectors corresponding to that, we're going to plug it in to the minus lambda thing. So it's going to be 1 minus 1, 0, 2, negative 2 minus 1, and the answer column is always going to be 0, 0 for these. So we're left with 0, 0, 2, negative 3. Now, as you'll see, you should always get one row of zeros. Always. And that's because that's what the eigenvalue does. It makes it dependent. What that means is that you're going to get at least one row of zeros. Okay? So, now we have our one row of zeros. We can start solving, so we're left with 2x minus 3y equals 0, or 2x equals 3y, or x equals 3/2 y. Now, since we only have one equation and two unknowns, we're going to have infinitely many solutions, so all you need to do is pick one that's not going to make it trivial. What that means is you can't have 0, 0 as your eigenvector. So we're gonna pick, I always pick a y, so y is gonna be arbitrary, and we're gonna set it equal to 2. I'm gonna set it equal to 2 to cancel out that fraction, so that means that x is 3. So that means our eigenvector, so that's how I write it, little vector symbol on top, eigenvector 1 is gonna be 3, 2. Okay, so that's our eigenvector corresponding to eigenvalue 1. Now, we do the same exact thing for eigenvector 2. So, we plug in our eigenvalue 2. It's going to be 1 minus a negative 2, 0, 2, and negative 2 minus a negative 2. So now this is going to give us 1 plus, that's 3, 0, 0, 2, 0, 0. So you see these are multiples of each other. If I did, if I divided the first one by 3, the second one by 1, we'd get the exact same thing. So let's just do that, and we're left with 1, 0, 0, 1, 0, 0. And now I can easily do row 1 minus row 2 equals row 2. So as you can see, we're left with our 1 row zeros like we're supposed to. Alright, so in this case, we know that x equals 0 and y equals arbitrary, so just pick any value that's non-zero. In this case, I'm going to pick 1, so that means our eigenvector 2 is going to be 0, 1. Now, you can get 0, 10, 0. You can have y be anything, as long as it'll still be a multiple of the one I have. So that is exactly how you find the eigenvectors for all functions. It gets a little tricky with a 3 by 3, so they'll give you a characteristic polynomial just like this. That's what this is. And then we'll use synthetic division, or they may just give you the actual answer. Or, yeah. Now we use synthetic division with the hint they gave us. It's going to be negative 1, this is going to be 2, this is going to be 4. Then this is going to be 8, this is going to be negative 3. And this is going to be 6, and this is going to be 0. So that means it worked, so we're left with lambda plus 2, negative lambda squared minus 4 lambda minus 3, or we can factor out a negative 1, lambda plus 2, lambda squared plus 4 lambda plus 3. So this would be lambda plus 3, lambda plus 1. Then eigenvalue 1 would be negative 2, eigenvalue 2 would be negative 3, eigenvalue 3 would be negative 1. Alright, so now we have our 3 eigenvalues. All we have to do is plug it into our matrix with the lambda subtracted. So let's do eigenvalue 1, we're left with negative 2 minus a negative 2, negative 3, negative 4, 0, 2, negative 5 minus, and sorry about that. Come on, computer, don't be struggling on me right now. It's struggling. Alright. Negative 5 minus a negative 2, and negative 2, negative 2, 0, negative 1, 3, 1 minus negative 2, 0. And then here we're going to be left with 0, negative 3, negative 4, 0, 2, negative 3, negative 2, 0, negative 1, 3, and then it's going to be a 3, 0. So as you see, this one's already a 1, so I'll make this. So what we're going to do here is we're going to start row reducing, try and get to row echelon form, and then everything will fall into place, I promise. Alright, so now that we're here, Let me do 2 row 1 plus row 2 equals row 2. We want this to be a 0. So -1, 3, 3, 0. And then -2 plus a 2 is 0. -6 plus a -3 is -9. And 6 plus a -2 is 4. 0. And left with, wait, hold on. Yeah. What am I doing? Oh my god. 2 plus a 0, -2 plus a 0 is 0, plus a 2 is 0, and 6 plus a -3 is 3, not -3, and then 6 plus a -2 is 4, and then we're left with 0, -3, and -4. As you can see, row 2 and row 3 are opposites of each other, so we can just do row 2 plus row 3 equals row 3. We're left with -1, 3, 3, 0, 0, 3, 4, 0, 0, 0, 0, 0. So from here, we already get a row of zeros. That's great. So now that means we did something right. Now we can start plugging stuff in. So 3y plus 4z equals 0, or y equals -4/3 z. Z is going to equal an arbitrary value, and in this case I'm just going to set it equal to 3, and that makes y equal to -4. Now we have -x plus 3y plus 3z equals 0, or x equals 3y plus 3z, which is -12 plus 9, which is 3, -3, sorry. So then our eigenvector 1 is going to look like this, -3, -4, and 3. So that is our eigenvector 1. Let me do one more just so y'all get the hang of it a little better. Let's plug in eigenvalue 2. It's going to be -2 plus 3, -3, -4, 0, 2, -5 plus 3. And it's plus because it's a minus and negative. That's why we're wondering. Alright. Now we can start solving the system. What the heck is going on with you, computer? Stop being silly. It's going to be 1, -3, -4, 0, 2, -2, -2, 0, -1, 3, 4, 0. Alright, so 1 is in the top left corner. That's good. That's what we want. Now let's try and make these 0. So I'm going to do row 1 plus row 3 equals row 3. We'll just do one step at a time so we don't get lost. No one gets lost. No child left behind. 2, -2, -2. Yeah, okay. And then 1 plus a -1 is 0, -3 plus a 3 is 0, and -4 plus a 4 is 0. So look at that. We got a row of zeros. Perfect. We still don't want this nasty system, so we want this to be a 0. So let's try and get that to be 0. So -2 row 1 plus row 2 equals row 2. 1, -3, 4, -4, and then we're left with -2 plus 2 is 0, and 6 plus a -2 is 4. 6 plus a -2 is 4, and then 8 plus a -2 is 6. Awesome. So now we're left with 4y plus 6z equals 0, or y equals negative 6z over 4, or 3 over 2, negative 3 over 2z. So then z is going to be our arbitrary, and I'm going to set it equal to 2, and that would mean y equals negative 3. Plugging that into our top equation, x minus 3y minus 3z equals 0, or x equals 3y plus 3z, which is gonna be negative 9 plus 6, which is negative 3. So that would mean that our eigenvector 2, so eigenvector 2 is going to be negative 3, negative 3, 2. Alright, so we got our eigenvector 1 and 2. I guess I'll just do the third one just for kicks, just for funsies. So negative 2 plus 1, negative 3, negative 4, 0, 2, negative 5 plus 1, negative 2. Again, it's plus because it's a negative eigenvalue, so the minus and the negative cancel out to give you a plus. Alright, so now that we have that, we get negative 1, negative 3, negative 4, 0, 2, negative 4, negative 2, 0, negative 1, 3, 2, 0. So from here, we already have a 1 on the top left corner. We can multiply by a negative 1. So it's negative row 1 plus row 2 equals row 3 equals row 3. So negative 1, negative 3, negative 4, 0. This stays the same. 2, negative 4, negative 2, 0. And now 1 plus negative 1 is 0. 3 plus a 3 is 6. 4 plus a 2 is 6, 0. Now we want this to be a 0, so we're going to do 2 row 1 plus row 2 equals row 2. We're left with negative 1, negative 3, negative 4, 0, 0, and then negative 6 plus is negative 10, negative 8 plus that is negative 10, 0, 0, 6, 6, 0. I don't know if you can tell, but row 2 and row 3 are multiples of each other if we divide by negative 10 and divide by negative 6. So I'm just going to divide by stuff right here. So I'm going to make this a positive. It's going to be 1, 3, 4, 0, 0, 1, 1, 0, 0, 1, 1, 0. So row 2 minus row 3 equals row 3. We're left with 1, 3, 4, 0, 0, 1, 1, 0, 0, 0, 0, 0. So you get row 0, so you're doing something right. So y plus z equals 0, or y equals negative z. Z is going to be arbitrary, so we'll set it equal to 1. So then y equals negative 1, so then x equals negative 3y minus 4z, or x equals 3 minus 4 is negative 1. So eigenvector 3 is going to be negative 1, negative 1, 1. Alright, and that is how you get your eigenvectors for a 3 by 3. Quite a bit of work, but not too bad. Alright, singular and non-singular. And this is just kind of like, I'm just going to explain this little matrix, this little table. So here we have determinant of a matrix is equal to 0. The determinant does not equal 0. So here it's going to be singular. Alright, so if you ever have a question saying, oh, this matrix A is singular, that means it is blah blah blah, and that means that it falls into the left hand side. And of course, if the determinant does not equal 0, it's non-singular. If it's non-singular, it is the determinant does not equal 0. They're interchangeable. Alright, so determinant equals 0, that means that they're linearly dependent. Linearly dependent. what that means is you're going to get at least one row of zeros when you row reduce, like what we were doing. Like when you plug in, when you get eigenvectors, they're linearly dependent. You're always going to get at least one row of zeros. Now, non-singular means that they're linearly independent. That means when you row reduce, you're not going to get a row of zeros. So when this, that means there's either infinitely many, or no solution. Let's just this over here. Alright, so infinitely many or no solution. That's what the determinant is equal to 0. Now what that means is, okay, so you know how we get a row of zeros at the bottom? So we have our little squigglies here. Squigglies being numbers. Alright, so this means it's dependent, right? Now, depending on what the answer column looks like, if the answer column ends up with a 0, we have infinitely many. Now, if, same situation, squigglies, if we get 0, 0, 0 here in the XYZ matrix, but we have a number that is not 0 here, any number, then you have no solution, because it's impossible for 0x plus 0y plus 0z to equal anything other than 0. So that's why it's infinitely many or no solution. Now, this one is going to have a unique solution. So it's going to have one solution that there's only one way that it's solved or solvable. So here we're also going to have at least one lambda is going to be 0, and here no lambdas equals 0. Now, another neat little thing, the determinant of A, let's say, is equal to the product of its lambdas. So let's say it's a 3 by 3, so it's lambda 1 times lambda 2 minus lambda 3 is equal to the determinant of A. So you see, if the determinant of A is 0, at least one lambda has to be 0 for that to work. And that's pretty much